Okay, everyone, let's try this again. I decided to record this so you have it and not lose time today when had a little uh, technical difficulties getting us and collaborate then over to Zoom and shortened session in Zoom. So let's go through this, and we're talking about Chapter 9, Covalent Bonds and Molecules. And again, suggested problems are posted. Very advisable to go through them, try to get them, ask questions next time we look at those problems, and we'll have a review session before our next exam that will happen on the 16th, and that's chapters 8, 9, and 10. Earlier today we did go over some chapter 8 problems, and they'll be posted to look at, but you should do the suggested problems. So let's talk about covalent bonding and molecules. Some of this we did earlier when we talked about in the first few chapters. We did go through this, so a lot of it should be familiar, and then we move on to a little more detail about the bonding in molecules. We'll talk about this because most important biological molecules for sure are covalent molecules. Covalent bonds, covalent molecules. We're talking about non-metals that participate in bonding, and they're between two atoms, but it could be among multiple atoms, of course. But we talk about the bonds between two. It occurs with non-metals, and why they do this, driving force of all bonding is to satisfy the octet rule. That is eight valence electrons satisfying or completing their s and p, the outer s and p orbitals. Here's the first example: two chlorine atoms. They come to the party with 7 electrons each. Remember, they're in group 7A. If you don't recall the main groups, we'll mention them again here, but you should review some of that if you've forgotten that. So the chlorine comes with 7. It's not happy. It needs 8 to complete its octet. So 2 chlorines could get together, and they both share 1 electron, and then they'll have they both feel like they have the 8, the octet. And of course, when they're sharing, the way that we write that when we have a sharing is a single bond between them, and this single bond implies that there's 2 electrons, a pair of electrons there. And what we're doing here in showing the valence electrons, those are called the Lewis structures or Lewis dot structures. They're showing the arrangement. And when we talk about arrangement of atoms and bonds, Lewis dot structures is the way that we show them and understand them. So what about between two oxygens? Oxygens come with 6 valence electrons. This are in group 6A when we look at the periodic table, and they need to share two electrons to get their 8, and they do that by both putting in 2 electrons, and then they get 2, they share 2. So when we look around, each of the oxygens is 2, 4, 6, 8. Remember, each line is 2 electrons, and both oxygens feel like they have the 8. And for nitrogen comes with 5 valence electrons. It's from it's in group 5A, and recall one of our earlier classes did show this when we talked about the diatomics. The 7 diatomics, they're all gases. Remember Professor Brinkelhoff from Diatomica. That's an acronym for all the 7 diatomics. Okay, nitrogen shares 3 pairs of electrons, and then in effect each of the nitrogens feel like at any one time that they have 8 electrons. 2, 4, 6, 8, and the same for the other nitrogen. Hopefully so far this is pretty much a review. Now another feature, these, what do we call these things? This is definitely the single bond. The single bond, covalent bond. And these, we have a special name for those electrons. Those are lone pairs. You can see that each chlorine has 3 lone pairs around it, right? Here's carbon dioxide. Carbon comes with 4 electrons, 1, 2, 3, 4. If we were to draw the Lewis dot structure, it would be carbon with dot, dot, dot around it. 4 electrons, it's in group 4A. And the oxygens come with 6 electrons, 1, 2, 3, 4, 5, 6. And we've already arranged it to form a nice symmetrical carbon dioxide. The carbon has, in effect, feels like it has 2, 4, 6, 8. That's nice. It has its octet. And the oxygens have 2, 4, 6, 8. Each of them has the octet. And you'll notice that it has shares two bonds with the carbon and has 2 lone pairs. Water, we can draw the Lewis dot structure for water also. The oxygen comes with 2, 4, 1 more, 6, 5, and 6, and the hydrogen comes with 1 electron, and it puts it in there and shares a double bond. So the hydrogen is happy. It has 2 electrons filling its outer orbital. Hydrogens just have to complete a duet because they just have 1 energy level, and you only put 2 electrons in the s, the first orbital. The oxygen still has 2 lone pairs, 2, 4, 6, 8, so it's happy also. And you'll notice this is drawn as a bent molecule. Later in this chapter we talk about the shape of molecules, and what influences the shape for water is these 2 lone pairs. They want their space. They take up space around here, and they push this single bond down a bit, making a bent molecule. There's exceptions to the octet rule. Just want to know there are some. Won't be ever asked to what are the exceptions. Just want to point out in the case of boron trifluoride, the boron, this is actually how it bonds, but if we look at boron, it's got 2, 4, 6. It's actually an incomplete octet, but that's what the molecule looks like, so it's an exception. And in the case of phosphorus trichloride, here's the one that we would draw. Phosphorus comes with 5 valence electrons, 1, 2, 3, 4, 5, and chlorine, each of the chlorines come with 7. They do the sharing, and that's the kind of regular complete octet. But it also can form this molecule with 5 chlorines, or phosphorus pentachloride, and that's because it's able to expand some of those electrons from the d orbital to form an expanded octet. So these are a couple of examples. So drawing the Lewis dot structures allow us to add up the valence electrons, which is important in trying to draw what the molecule actually looks like. Now we have to recall this diagram, mentioned it earlier, the main groups. The main groups, we can predict how many valence electrons there are for each of the elements in the main groups. If you're in group 3A, you got 3 valence electrons. If you're in 7A, the halogens, you have 7 valence electrons. The noble gases have 8. They're not interested in bonding. They have all their valence electrons already. If you're nitrogen, you're right here. You have 5 valence electrons. So you got to know how to use your periodic table to tell how many valence electrons an atom of an element have. And we use that to put the atoms together, whatever we had, we were making up a structure so that we have filled octets. Now, when we draw molecules using the Lewis dot structure, we put the atom needing the most bonds in the middle as the central atom. And then we arrange them, after we do that, if we need to form double or triple bonds if needed. So we'll see examples here. So here's we're told this is the molecule nitrogen trichloride, and we would add up electrons. We would draw a framework, which we'll do here, and then make sure that the octets are filled on the outer atoms and the central atom. So here's nitrogen has 5 valence electrons. Get that from the periodic table. It's in 5A. Chlorines come with 7, so we add this up. There's 26 valence electrons. Okay, that's how many we have to work with. And now we're going to draw the framework of the molecule. Let's put nitrogen, its most needy, in the middle, and connected to the chlorines. So the chlorines each had 7. So if they have 1 bond, they're satisfied. They have their 8. The nitrogen came with 5. Well, if we make 1, 2, 3, that's 3 of the 5. And then there's 2 more, and we'll see that. Okay, there's a lone pair for the 5. And this is the complete Lewis structure for nitrogen trichloride. And if we were to count these up, there definitely should be 26 shown here. And you could check that, there are 26 there. So you will be expected to recognize a correct Lewis dot structure of a molecule if to choose among them on a multiple choice test. Okay, here's formaldehyde. So we'd count up. We have for the 4 from the carbon, of course, 4 valence electrons. The hydrogen has each hydrogen has 1 valence electron, so that times 2 is 2, and the oxygen has 6. 12 valence electrons. That's what we have to work with. The carbon is the most needy. That's going to be the central atom in this structure. So we would draw this as the framework initially. Now let's check what we have here. The hydrogen is fine. It's got the 2 valence electrons to fill their duet. That's all they need. The carbon has 2, 4, 6. Okay, that's not enough. It's not a filled octet, so something needs to be changed here. The oxygen has there's 2 there, and then it's got lone pairs. It's got 3 lone pairs, right? For the electrons it brings in 6. So what we need to do is to arrange some things here. Okay, so the carbon needs 2 more electrons. So what happens is we move 2 electrons and make this a double bond. And now the carbon has 2, 4, 6, 8. It's happy. The oxygen still has 2, 4, 6, 8. So that's the correct structure, Lewis dot structure of formaldehyde. So that one was a little bit of twist there for hydrogen. Hydrogen's the simplest we could think of, and each hydrogen comes with a proton and 1 electron. It's not happy on its own, and if hydrogen had to stand alone, it's going to be diatomic. It's going to be N2, and that's how that happens, right? So the hydrogen just has 1 energy level. First energy level, all it needs is 2 electrons. Oh, a polyatomic, we should recall, we had lists of them, and you just need to really recognize when a polyatomic is present. But we also, now we can go one step further and understand why a polyatomic has its charge. And we'll look at some examples of polyatomics and how they got their charge. So you remember polyatomic, well, it means multiple atoms and they're ions. So it's a particular case. So here's the only positive polyatomic cation, if you remember, ammonium. And that's its structure, and that's its formula, and that's its name, hydroxide, nitrate, etc. We have a bunch of them here. Now we'll talk about identifying what's the correct, how do we get to these correct structures here with the charge being placed in a particular place. How we do that is examine the formal charges of each of the atoms in a polyatomic, and so we'll do that right now. Formal charge, we calculate that for every atom in these polyatomics, and we do that by counting the knowing what the valence electrons of the neutral atom is. That is to start with. For example, if we were to say carbon, that's 4. If it's hydrogen, that's 1. If it's oxygen, that's 6. So that's just knowing the valence electrons right from the periodic table. We subtract the number of covalent bonds in the molecule, the ion in this case that we're talking about, and then subtract the number of unshared electrons. So the unshared electrons, those are from the lone pairs. Okay, so some examples. So this is hydroxide ion, right? You'll never have to really name this per se, but you might already kind of recognize it. It's always given to you in a table, OH -1. But now we're going a little further to understand where that charge comes from. Okay, so let's figure out the formal charge for each of the atoms here. First, for the hydrogen. So the hydrogen has 1 valence electron. In this case, how many covalent bonds are there? Well, there's 1. It's participating in 1. And unshared electrons, there's 0. There's no unshared electrons. Okay, so that comes out to 0. So if its formal charge is 0, do the same thing for oxygen. Oxygen has 6 valence electrons where it's neutral. It's got, in this case, it's got 1 covalent bond, and how many unshared electrons are there? There's 6, 2, 4, 6, and what does that equal? 1, -1. And now what we're going to do is we'll add these up, 0 and -1, and that's how this polyatomic gets the 1- charge. another way to write that is just putting the minus in a circle, another convention. So for oxygen, if we would do this analysis, we would see that's a neutral for water. This is hydronium ion. If we were to do the analysis, we'd come up with a positive there. Hydroxide ion we just did. And we could see this series also. This is NH2. NH2, if we would do the analysis of formal charge, we'd get a -1. If we did the analysis for ammonia, NH3, we'd come up with a 0 formal charge overall, neutral. And if we would do that analysis for ammonium, the only positive polyatomic that's commonly discussed in general chemistry, we'd come up with the plus. Okay, here we're going to analyze, look at this sodium azide. Sodium azide, really important molecule. It's actually how most conventional airbags work. They have a certain amount of this in them, and then when a reaction is started or catalyzed, this is a solid, sodium azide, well, there's a sodium, and when it's catalyzed, it immediately, very quickly forms nitrogen gas, N2, to fill up our airbags. Okay, calculate the formal charge on each atom. What's the overall structure of azide? Okay, so we look at the nitrogen here. It comes with 5. How many covalent bonds are there? 1, 2, 3, 4. How many unpaired or unshared electrons are there? Well, there's 1, 2, 3, 4. There's none. All right, so all the electrons are being used here. So we get a +1 formal charge. Then we look at this nitrogen. It comes with 5 again to start, 5 of the neutral. Let's see how many covalent bonds. There's 2 there. And how many unshared electrons? There's 4. We come up with a -1. Well, we do the same for this one. And so this would be the charges on each of the atoms. So what do you think the overall charge is of this azide molecule? Well, it would be a -1. You could see that, right? These two cancel out. We'd have azide, N3 is a -1. Pretty important molecule for our airbags. So drawing the loose dot structures for the polyatomic, well, we just did the formal charge of them, and it's similar to how we would draw a Lewis dot structure for neutral molecules, but we'd consider the charge there. So for hydroxide, we know that that's what it is. And how many electrons does it come with? 6. And this came with 1 electron, and there's one more electron somewhere floating around because it has a minus charge. So there's 8 valence electrons overall. Okay, so what about nitrite ion? It comes with 5 valence electrons. And what about this oxygen? Each of them come with 6, and then there's 1 more electron because there's a minus. So that's another electron. So how many electrons? We have 18 electrons. Go through the same procedure here. We just summed up the valence electrons. Now we draw a framework. well, the nitrogen is the most needy in terms of the bonds that it needs. It comes with 5. The oxygens have 6, so we put that in the middle. So now we start filling in the electrons how we'd expect them to be, at least initially, then we'll reconsider. So how many we have now is 2, 4, 6, 8, 10, 12, 14, 16, and there must be 2 more electrons over there. There it is. Okay, so now let's consider the octets of the outer electrons, of the outer atoms. 2, 4, 6, 8. 2, 4, 6, 8, that's fine. 2, 4, 6. Okay, nitrogen does not have its octet. Something has to change. And we also are not showing where the minus sign is. So how about this? 2, 4, 6, 8. Okay, so now that nitrogen has the 8, 2, 4, 6, 8, this oxygen still has its 8, so this looks like a pretty good structure. And so 2, 4, 6, 8, we probably need to put the charge on this this side of the molecule. That's where the most electrons now are hanging out. And this oxygen feels like it has an extra electron. Okay, phosgene. Phosgene, you may have heard of that. It's a pretty poisonous substance. It is very dangerous in the lab. Sometimes it's an off reaction forms phosgene. Phosgene was used as a chemical war agent in the past. Really toxic stuff. So let's look at it. We have carbon, oxygen, and 2 chlorines. So what do we think? Well, carbon, of course, needs the most electrons. It comes with 4. Oxygen came with 6, and chlorine has 7 already. So we would kind of draw this structure first. Carbon in the middle. The chlorines out there. So we added up all the electrons and they're all there. Now we check for the outer atoms. They have 8 and 8 and 8. Then we check the central atom. Not good. So carbon has 6. Something has to change here. Probably involves moving a pair of electrons. And by doing that, by putting 2 electrons over here, so that carbon now has an opportunity to have 2, 4, 6, 8, and now it's pretty happy, and so we'll go with that. Now, there could be another way to draw this. The chlorine could contribute 2 electrons and make a double bond over there, so that's possible. And it does turn out that sometimes there are more than one possibility of how electrons are shared, where all atoms have their octets. Sometimes there's more population of one or the other just because it's more stable, but there are multiple structures sometimes that could be drawn that are valid. And it turns out this is the more stable one, because this is more energetic to keep a separation of charge. So just to know there could be multiple forms, but this one, the way we drew it first, works out the best. This is possible but very unlikely because of this separation of charge is more energetic. If you'd add energy here, you might push it to form more of this this structure. So what we just hinted at is more than one form of a given molecule, and that leads us into resonance structures. So resonance structures are the possibility of slightly different forms of a given molecule. So here's our nitrogen dioxide, and if we would draw more of a ball and stick, it would be like this. It happens that double bonds are shorter than single bonds, and the charge, because the electrons are more populated over here, it's got the charge is likely to be concentrated over here. But that's not the only way that this could be shown. So actually, this double bond can be moved from this one to here, and then back again, and that's resonance. It's resonance. So actually, it balances out. It's more stable by equilibrating the charge among all of the atoms. So resonance structures. Just to know, resonance structures, more than one way of drawing a given molecule. And we're showing it in equilibrium, go back and forth. And this is the average of those two, resonance structure. That double-headed arrow means equilibrium, go back and forth. So what we just saw there, it spread out the charge among more of the atoms in the molecule. For instance, here's a set of 4 different resonance structures for phosphate. They don't look that much different because it's one oxygen having a double bond, the other having a single bond, but it is actually a different oxygen having that double bond. This actually, when it has more resonance structures, it makes a more stable molecule or a more stable ion. And that's what these polyatomics all have, a certain amount of resonance, and that's what makes them very stable. Look at nitrate, and so we'll draw what if we use our number of electrons and place them around. It looks like there's charges on the nitrogen and the oxygen. And there could be multiple forms of distributing that charge among these different structures. So I'd like you just to be able to recognize and know that resonance structures exist, and it's a way to make molecules or ions more stable. If possible, they move around some of the pairs of electrons. And so next we segue into shapes of molecules, and so this is pretty interesting, and it relates to where we just drew these pairs of electrons and how that impacts the shapes of molecules. And this is a place we'll stop right here. I hope you have a chance to review this video up to this point, and we'll take on shapes of molecules in our next meeting. Remember that there's always posted suggested problems, and I hope that you are taking the time to review them, and because it preps you to be able to think through and ask questions in our live session to relieve yourself of any kind of mysteries and questions, and confirm your understanding of the material we're going through. So this is chapter 9. We're in the latter part of chapter 9. We'll pick up shapes of molecules next class.